Now that you've learned how to take the derivatives of a lot of basic functions, learned how to handle adding and subtracting functions and their derivatives, and also scalar multiples, we have to look at a few special situations like products and quotients, where unfortunately things don't work out as nicely as they did with adding or subtracting. You might remember that if you add two functions and want to take its derivative, you can just take the two functions' derivatives separately and add them together, and the same works for subtraction. But it won't work for multiplication. If you want to check that out, try doing x squared times x. Let's take the derivative, see if you get the same as if you took the derivative of x cubed, and you'll find out very quickly that you don't. So it turns out there's a bit of a complicated rule for the product and quotient derivatives. We call them the product rule for the derivative of a product and the quotient rule for the derivative of a quotient. Both of these rules are based on the limit definition of the derivative, and there are plenty of proofs out there of how that limit definition works to come up with this formula. But right now, I just want to sort of show you the formula so you can work on memorizing it and learning how to use it, and then give a few examples to show how, in fact, you would use it. Now, here you have the product, f times g, right? And if you want to take the derivative of that, right, it turns out that it's going to be f times g prime plus g times f prime. Now, the order here doesn't matter too much because multiplying and adding, and if those operations are reversed in any way, you'll still get the same result, right? Because multiplying and adding are commutative operations. But one of the ways that you can help memorize this is you take the first times the derivative of the second plus the second times the derivative of the first. It's a little bit more informal, but it's easier to memorize. The other thing is, while this looks fairly complicated, it's got a lot of symbols, if you remove the parentheses x, right, then it reduces very quickly to just f g prime plus g f prime. That's a lot easier to memorize. I think your best bet for memorizing this is either to think about the written description or the fg notation without all the x's. So here's an example. If you wanted to do the derivative of x cubed over e to the x, you could think of the x cubed as f, and you could think of the e to the x as g. You will have to be able to identify that this is a product, in fact. Right? But when you see x cubed e to the x, we know that means x cubed times e to the x. So when you go to take this derivative, right, you have to take the derivative of the first, which is just 3x squared, times the second, which is e to the x, plus the second, which is e to the x, times the derivative of the first. I did this backwards. Okay. My brain sort of kicked in and did this in the opposite order, but it turns out that it really doesn't matter. So let me do it again, following the rule that I just gave you in the order I gave you. Right? I said I'm going to do the first times the derivative of the second plus the second times the derivative of the first. Okay? Now, as far as the derivative goes, the calculus part of this step is over. Hopefully, you're getting comfortable with the fact that e to the x is both the function and the derivative. However, we want to try to simplify these derivatives whenever possible. Something you'll see in the future that we'll be doing with derivatives is setting them equal to 0. It would be pretty meaningful and pretty important. So factoring and looking for common factors is always going to be a good step. When you look at both of these terms, hopefully you can see the x squared and the x cubed have some common factors, and you can also see they both have a factor of e to the x. So you can actually factor out an x squared e to the x from both of these, and that would leave you with an x plus 3. Okay? And then if we were looking for horizontal tangents like we've done before, we now have a product of three things. Any one of them could be 0, which would make the entire product 0. Okay? So first we have to learn what the product rule is. We have to remember that when we multiply functions and try to take the derivative, we can't just take the two derivatives and multiply them together. And then we actually have to be able to put it into practice and finish it with that example under your belt. It should hopefully get a little bit easier. Okay, so now that we have one of these under our belt, let's try looking at another example. When you see sine of x times cosine of x, even if that dot wasn't there as a multiply, you should hopefully recognize that this is another product. Again, we can call this one f, we can call this one g. And even though the rule is not in front of us, you'll get to know it, and pretty soon you'll be doing this without even thinking about it. So don't worry too much about memorizing it and thinking that it's going to be a very difficult thing to do. If you get used to saying first times the derivative of the second, second times the derivative of the first, it becomes pretty easy to do. Plus, in this case, as long as you match each function with the other's derivative and add them together, you can't really go wrong. So even though I had them out of order, it was still going to work out just fine. So I'll do this one in the order I suggested. First times the derivative of the second plus the second times the derivative of the first. Okay? Now again, what ends up happening a lot of times in calculus is we can do the new material just fine, but then it's the following up with the simplifying. And that's because we have to remember everything we've ever learned over the course of all our algebra and pre-calculus semesters. I'm going to rewrite this as cosine squared of x minus sine squared of x. When I have one negative term and one positive term, I usually put the positive term first. That way it's just a few less symbols. And this is a perfectly fine answer, but you might also recognize this as a trig identity, and you might see in the back of the book that they wrote it this way. It's fine. It's not wrong to leave it as this, and I'm pretty sure that this semester, since we're not using a lot of trig identities, I know I'm certainly fine with this. You'd have to see if your teacher wanted you to know those trig identities and simplify it. Just wanted to look at one other example here before you get into practicing the product rule on your own. In a case like this, you certainly could think of this as a product rule, right? F times G. That's not how I would go about doing this problem. It overcomplicates things, right? If you actually can multiply things out, I would just go ahead and call this x to the 9th. Now this is really x to the 1/2. Oops. That's really x to the 1/2. And if you multiply x to the 6th times x to the 1/2, you're going to get x to the 6.5, which is 13/2, plus 3x to the 6th. Now, I haven't taken the derivative yet, because by rewriting f of x, I didn't have to use the product rule. So now I can take the derivative using just my basic subtraction, addition, power rules, constant multiple rules, right? 9x to the 8th. Minus 13/2 x to the 11/2, right? Because I subtracted 1, plus 18 x to the 5th. And that would be it. You could probably do some factoring, but it's not going to get all that much prettier here. So, but the point of this example is just because you have a product doesn't mean you have to use the product rule if you can simplify it. But hopefully you'll notice in the previous examples, no simplifying was possible. So make sure you practice some product rules. If you're not comfortable doing the derivative in your head, you could always write it down as a placeholder with the derivative sign or symbol, and then take the derivative on the next step. But at the beginning here, most of the examples will be very easy to do straight derivative rules.